Hello everyone. In this video, let us see how to use transfer learning. We are going to see the classification of SVHN using transfer learning from pre-trained MNIST CNN. So first of all, we have a basic knowledge on, not basic knowledge, complete knowledge on how MNIST looks like. So let us look into how this SVHN data set look like, right? Yeah, you can see the data set over here. So SVHN is a real world image data set for developing machine learning and object recognition algorithm with minimal requirement on data pre-processing and formatting, and it is almost similar to MNIST. That's the reason we are using it on transfer learning, and also it incorporates an order of magnitude more labeled data over 6 lakh digit images, and it comes from significantly harder unsolved real world problem, right? So it is obtained from house numbers in Google Street View images. So SVHN means Street View house numbers, right? So let us look into the overview of this data set. There will be 10 classes, one for each digit. Digit 1 has label 1 and label and 9 has label 9 and 0 has label 10, right? So 73257 digits for training and 26,032 digits for testing, and 5,31,131 additional somewhat less difficult samples to use as extra training data. And also it comes in two formats. One is like original images with a character level bounding boxes, right? Character level bounding boxes, and the another one is like MNIST, like 32 by 32 images centered around a single character, right? So many of the images do contain some disruptors on the sides that you can see over here, right? So here these are the original variable resolution color house number images with a character level bounding boxes. So you can see some bounding boxes over here, right? So the blue bounding boxes are just for illustration purposes. The bounding box information are stored in digitstruct.mat. So instead of drawn directly on the images in the data set, right? And then each star.gz file contains the original images in PNG format together with the digitstruct.mat file. And so this is not really important, so just let me show you both. And here you can see that the character level ground truth in an MNIST like format, and here all the digits are resized to a fixed resolution of 32 by 32 pixels, and the original character bounding boxes are extended in the appropriate dimension to become square windows. So resizing them to 32 by 32 pixels do not introduce the aspect ratio distortions, and this pre-processing introduce some distracting digits to the sides of the digit of interest, right? So now let us look into this one, right? So let us try to understand the data set. So now the data set understanding is very clear. So now let us look into the code, right? So first step is that we have to import Keras modules, right? So what are we importing? We are importing Keras, and from Keras.datasets we are importing MNIST, right? So that is what we are going to do, transfer learning, right? So basically what we are going to do, we are going to do classification of Street View house number, and already we have the pre-trained model of MNIST. So using that we are going to do transfer learning now. So that's why we are importing MNIST now. From Keras.models import sequential, and then import dense, dropout, flatten, conv 2D and max pooling 2D, right? And then I'm importing or loading the data set. It is in H5 file, so import H5py, import numpy as NP, and this is where the data is there. And I'm loading the training, testing and validation data. And x_train, y_train, x_test and y_test. Don't forget to close this file, right? So now let us visualize the data set using matplotlib, right? So we are using the matplotlib. You can see here width and height and the columns and rows is given, and it is being done with the help of for loop, right? So this is how it looks like. And let us look into the shape of the training data. It is 42,000, 32, 32, and the data type is actually float 32, right? So what are we going to do now? We are going to resize all the training and test inputs to 28 cross 28 to match with the MNIST CNN model's input size, because basically this MNIST is 28 cross 28. So what are we going to do? We are going to resize it. For that, we are importing CV2. CV2 is nothing but OpenCV module that is being used for resizing the function, right? So we are resizing the data set for training and testing inputs with the corresponding size, right? So here we are resizing it to 28 cross 28. Clear, right? So we are resizing it to 28 cross 28, and the data type is float 32, right? So when you do that, like now look at the shape. Now it is showing that 28 28, right? So this is X training, this is the X test, right? So it is clear now. So what are we going to do now? We are going to reshape train and test sets into shapes compatible with the Keras models, right? So the Keras expects in certain format. So we are giving input image dimensions as 28, 28, right? Keras expects the data to be in that format, like NE means number of examples. This is number of height, number width, and then NC is very simple, number of channels, right? So this is what we are doing. And then we have to normalize the data set like all the other cases, so that the output will be ranging from 0 to 1, right? So we are like normalizing the input now. And then we are giving the batch size, number of classes and epochs. So batch size, I have chosen it to be 128, number of classes 10, epochs at 12. And then we are printing it, right? So now we have to convert the digits to 1-hot vectors. Yes, we are doing that. And once we do that, we have to build the CNN. So for that, we have to define the layers with the model with the same size of the CNN that is being used for MNIST classification. So we are going to give appropriate names to each layer and to access them later, right? So what are we doing now? We are using model is equal to sequential, right? Model is equal to sequential, and then we are adding convolution, kernel size, and then the kernel size is 3 cross 3 over here, and then activation is ReLU, and then convolution 3 cross 3, and then here the activation is ReLU, and then maximum pooling of 2 cross 2, and then dropout 0.25, and then we are flattening it. Then the fully connected layer with this 128 neurons, and activation is ReLU, and then we are applying dropout with 0.5 probability, and then fully connected layer with how many units we are using? 10 units, and activation functions as softmax, right? So basically here we are writing that number underscore classes, right? So we are going to freeze the initial convolution layer weights and train only the dense layers, right? So we are going to freeze the layers in the model which do not have dense in the name. Which one we are going to freeze? Which do not have dense in their name. So if you check into this, what are we going to do here, right? So we are saying that for layer in model dot layers, print colored layer dot name into blue, and then trainable into red. So that you can see over here. So now we have to load the pre-trained weights from the MNIST CNN model. So we are loading the weights from that model. The pre-trained weights must, we can have it in the folder, and that we can use it over here. And then we can set the optimizer. So here the optimizer what I used is Adam. And the last what I have used is categorical cross entropy. And for Adam, it is always better to go with the learning rate 0.001, right? And that is why I have chosen that, right? Now I'm compiling it with a loss categorical cross entropy. optimizer is optimizer in the sense it's going to be adder, and then matrix is equal to accuracy, right? Now the training can be done. So we are going to fit the model to the SVHN data set, right? We know the batch size already, epochs already given, verbose we are choosing it as 1, and then we are training on the data set. Now if you look into this, we are getting around 89.87, accuracy is 75.20, right? But if you have not done all these, and if you have tried with the accuracy, definitely it is going to be very low, right? So if we evaluate the CNN model, what we can say is like loss is around 0.513 and the accuracy is around 0.853, right? So in case if you want to do some predictions, you can use it like using the matplotlib, you can check. Now see, it's showing that this is 9, yes. So the label is also saying that it is 9. So 2, 2, 1, 1, 9, 9, 5, 5, right? So in case if you want to save the train weights and model in H5 files, you can save it out so that you can set the path where you want to store the model and weights. Clear with that, right? So very simple it is. So let us meet in the next session.